Section 9.3, applying the ideal solution model to a binary solution. So in a binary solution, the vapor pressure over here, P total, that's the vapor pressure of two components. So that's P1 plus P2. And then we use Raoult's law. P1 is X1 times P1 star. P2 is X2 times P2 star. P1 star is the vapor pressure of pure 1. P2 star is the vapor pressure of pure liquid 2. So we have this P total over here in a different expression. X2 is 1 minus X1 because it's a binary solution. So X1 plus X2 is 1. And then we can say P total is linear with X1. Also, you can express P total as a function of X2 if you want. So you just need to rewrite this X1 as 1 minus X2. And then in that case, P total is P1 star plus P2 star minus P1 star times X2. You just swap every 1 with 2, every 2 with 1. And again, X is the mole fraction of 1 and 2 in the liquid phase. What about the gas phase? We use Y1 and Y2. Y is the mole fraction of the species in the gas phase. And therefore, Y1 is just P1 over P total. And P1 is X1 times P1 star. That's the Raoult's law. Similarly, Y2 is P2 over P total. And P2 is X2 times P2 star. So that's understandable. The partial pressure of 2 is proportional to the mole fraction of 2 in the liquid phase. When you have 100% liquid 2, then this guy is simply P2 star. So we can use Y1 divided by P1 star. So over here, Y1 divided by P1 star, that's X1 over P total. Similarly, Y2 over P2 star is X2 over P total. Why do we do this? If we sum up this two, we can see the result is 1 over P total. So it's kind of interesting. It's a little symmetrical. P total is X1 times P1 star plus X2 times P2 star. So it's P total is X weighted partial pressure of X weighted pure pressure of 1 and 2. And now over here, the reciprocal of P total is the Y weighted reciprocal of pure pressure, pure vapor pressure of 1 and 2. Right? If it helps you to recognize the difference between this equation, okay, over here, this equation, and this equation, right? Other than X and Y, there's also a Z as the mole fraction of the two species in both phases. Let me give you a numerical example. Okay, let's say we have two components, A and B. In the liquid phase, you have 5 moles of A, 5 moles of B, and then XA is 0.5, XB is 0.5. Very simple. In the gas phase, I don't know, let's say you have 9 moles of A and 1 mole of B, okay? And then Y of A is 0.9, Y of B is 0.1, right? 9-to-1 ratio. But what about Z? Okay, when you're looking at Z, you need to look at the total number moles of A and the total number of moles of B. So for A, it's 5 plus 9, it's 14. For B, it's 5 plus 1, it's 6. And overall, there are 20 moles of species. Okay, 20, that's the total number of moles of A and B. And then the mole fraction of A overall is 14 moles of 20, that's 0.7. Z of B is 0.3. So you probably have realized the value of Z is between X and Y. So in the numerical example I give you, X of A is 0.5, Y of A is 0.9, and then Z of A is in the middle. It's 0.7. All right, and same for B. This Z of B is between X of B and Y of B. Well, but it does not have to be right in the middle. In my example, I intentionally give you just 10 moles of liquid and 10 moles of gas, just for simplicity. Now let's look at the phase diagram of pressure versus Z. So this is the pressure, this is Z. We're looking at the room temperature. Remember, the temperature is being held constant to make things easier. And then we're looking at benzene and toluene in this picture. So let's look at the liquid phase first. Under high pressure, the mixture of benzene and toluene is in the liquid phase. This is simple. There's only liquid phase, all right? Over here, this is 0% of toluene. Over here, this is 100% of toluene. So in this situation, you have 100% liquid phase. Now let's make it even simpler. Let's say we have 100% benzene. So 100% benzene. So liquid phase. Under higher pressure, it's in the liquid phase. Okay, but right here, about 90 bars, the vapor pressure and the liquid, the vapor and the liquid phase coexist. Actually, at this point, benzene starts to boil at the room temperature under this pressure. Okay, but what if the pressure is even lower than here, right here? Well, benzene exists in the gas phase. We can do same analysis along this line, 0% benzene, then 100% toluene. When the pressure is higher than 30 bars, it's liquid toluene. Lower than 30 bars, it's toluene gas. At 30 bars right here, they coexist. This room temperature becomes the boiling point of toluene under the 30 torr pressure. I'm sorry if I said bars. They should be actually torrs. 1 ATM is equal to 760 torrs, and 1 bar is 750 torrs. Alright, so over here again we are looking at the mixture in the gas phase. When the pressure is low, you just have benzene and toluene both in the gas phase, no liquid. Now this region in the middle, this is the more interesting region. Let's look at this point C. This point C, I think we have overall 70% benzene and 30% toluene, point C. So in this case, there are two phases. There's a liquid phase, there's a gas phase. And when you draw a horizontal line that crosses this point C, over here, you will get the mole fraction of benzene in the liquid phase. It's 45%. You will actually get the mole fraction of benzene in the gas phase as well, 0.7%. Maybe 0.74. In the middle, it's 0.7. Okay, now we have X benzene is equal to 0.45. Y benzene is equal to 0.74. Z benzene is 0.7. All right. Okay, so that's point C. Now let's look at point B. Well, same C value, Z benzene is 0.7, but over here you can see the pressure is higher. You have a higher pressure. Okay, on the higher pressure, now let's look at X of benzene. X of benzene is 0.65. Let's look at Y benzene. Y benzene is 0.88. Anyway, B is in the middle. Well, not right in the middle. B is between this data point and this data point. So this is really interesting. Even if we have a constant C benzene, over here, you have different X benzene, Y benzene, then this point B. So now let's describe this process from A to B to C to D. So at first we have A. It's in the liquid phase only. You have 70% of benzene, 30% of toluene, both in the liquid phase. There's no gas. Then we gradually reduce the external pressure to here. Alright, now it starts to boil. Actually, it starts to boil. And then at point B, you have some vapor, including both benzene and toluene in the gas phase. And also you have a lot of benzene and toluene in the liquid phase. Actually, more in the liquid phase than in the gas phase. Okay, so it's closer to the liquid phase. This B, point B, is closer to the liquid phase. And then you keep lowering the external pressure. Now this C is closer to the vapor phase. Now you actually have more vapor than liquid phase. So later you will see this segment give you the ratio of the number of moles of the vapor. This give you the number of moles of liquid. So the ratio between this and this is the number of moles of vapor versus number of liquid. So over here you have more vapor, less liquid. Over here you have more liquid, less vapor. All right, so and then we further reduce the external pressure at point D. Well, it's just 100%. Gas phase, in the gas phase, you have 0.7 benzene, 0.3 toluene. So again, this is just a benzene toluene ideal solution. Now let's just amplify this point B. I want to prove it to you. This part, this BV versus this BL, is equal to the number of moles of liquid versus the number of moles of gas. It may look a little strange because the liquid phase is here, yet this part is proportional to the number of moles of liquid. Alright, but you know, if we move this B up here, you have a long segment here and zero segment on the left hand side, and you understand that means you have zero number of moles in the vapor phase. That makes sense, right? So if you just look at this extreme case, you'll realize this segment is indeed the number of moles of liquid. But we can also prove it. We're going to prove BV over LB is the number of liquid over the number of vapor. V stands for vapor, L stands for liquid, B is just A, B, C, D, just a random data point. So how can we prove this? Well, make sure you understand this. This L point give you the mole fraction of benzene in the liquid phase. This V give you the mole fraction of benzene in the gas phase. And this B will give you the overall mole fraction, right? Okay, so this B is the overall mole fraction of benzene. So this B times the total number of moles of everything. This part should be the number of moles of benzene in the entire system, in both phases. And over here, this gives you the number of moles benzene in the liquid phase. Again, this L is the mole fraction of benzene in the liquid phase. So V is mole fraction of benzene in the gas phase times the total number of moles of everything in the gas phase. Alright, so this is a very simple equation, and then it's just algebra. You just move things around and then you get this equation from here to here. It's very easy. I'll let you verify this. B minus L, that's the length of the segment LB. V minus B, it's the segment of BV. Again, B minus L is this segment, and BV is V minus B. Alright, so and then look at this. This is a liquid, and actually this is the segment close to liquid. This is a vapor. This is a segment close to the vapor phase. However, well, we'll do this, cross multiplication. BV times total vapor equals the liquid times LB. And now you can see BV over LB is liquid over vapor. BV over LB is actually the number of, this is the number of moles of liquid. This is the gas phase. So that's why it's a little bit counterintuitive, all right? But you can prove this. If you can prove this, you don't have to memorize this.